Okay, so last speaker of the morning session is Sergei Mironov from Moscow. He's going to tell us about almost stable wormhole beyond Horndeski. Please start.
Thank you very much. So first of all, I would like to thank the organizers for the opportunity to talk. And also I want to apologize to the specialist here because I will have a big introductory part and maybe it will be boring to those who already know how to make calculation in spherical symmetric background in Horndeski series. But still, so well, first of all, I'm not sure I need a motivation to study wormholes. Everyone understands what it is. It's a teleport to some other place. Also, if a wormhole connects two parts of the same universe, it could be made into a time machine. And of course, if one wants to create a universe in the lab, it's also connected to our universe by a wormhole. So, well, but anyway, it is a nice example of non-singular gravitational solution. Unlike, for example, black hole, which have singularity and also horizon, we discuss wormholes that have neither. So, well, of course, wormhole solutions are known for a long time, and before that, there were speculations. So basically, there are two types of wormholes. The first one connects two different universes. It's like here. So we have two usually flat universes, which are connected by a narrow throat of wormhole. And another possibility is a wormhole that connects two parts of the same universe. This part could be infinitely far away, then it's almost the same as here, or they can be affected by each other. So in this case, it's much harder to construct such solution. But for any wormholes, there is a non-trivial feature that matter near the throat should violate the null energy condition. So if we take any normal matter, it always comply with it. So we need to use something strange. So at first, usually ghost scalar field was used. But the problem with such theories is that they're unstable in classical or quantum theory. In classical theory, there could be gradient instabilities and ghost law. I'll take on the next slide. So what are instabilities? So we take linear theory above our background. If we have additional fields, for instance, scalar field, we perturb it, and also, of course, metric. And then for each degree of freedom, after getting rid of all non-dynamical degrees of freedom, we supposedly come to such form of Lagrangian. And stability means that these coefficients, u, v, and w, are somehow constrained. So the dispersion relation for this degree of freedom is as follows. And stability means that u greater than 0, v greater than 0. And if we consider not only very high momentum, but all of them, also w is greater than 0. So, well, if u or v is less than 0, we get gradient instability. That means that solution for such equation is growing mode. And since it's growing for arbitrary high momentum, the background solution is destroyed instantaneously. And if both of them less than 0, that is ghost. On linear level, it seems okay. But when we have quantum theory, we have unstable vacuum, or if we have some interaction with another mode, which is not ghost, it is also catastrophic even in classical theory. W is connected to tachyon instability, and if we take the limit of high momentum, we care only about U and V. But generally for wormholes, we also need to care about this W, but it's much harder. Well, the answer for this coefficient W is much bigger, and it's hard to examine. So anyway, we start with high momentum regime. So as I told, there is no energy condition which we need to violate, and now I will briefly show why. So we study this type of metric. It's spherically symmetric. Generally, we can take B to anything we like due to reprogrammatization invariance, but we can keep it. And R runs from minus to plus infinity. Since we're considering wormhole solution, we have two universes which are connected with the help of wormhole. And the wormhole is non-singular, so we have this and this relation. So there is no singularity in metric and no horizon. So, and on the infinity, plus and minus infinity, we have asymptotic Minkowski. And this J is effective radius, which is bigger than 0 always. So a scalar field is also a function of radius. And let us examine the equation of motions. So this is G00 equals T00, and this is RR radial part. So if we combine them, we get such an equation. And let us see what it means. It means if we write this combination, so this one is effective radius. In flat, I mean Ricci flat case, it is just R. In standard matter massive case, it have some singularity, so it's 0 at some finite point. And in wormhole scenario, it is always greater than, for instance, 1. That doesn't matter. That's just schematically. So, and this point is the wormhole throat. So this combination in this case, for simplicity, we can take B equals to A, but it doesn't really matter. It always will have such a profile. So for flat case, it's just a constant because this is just a constant. And for our wormhole scenario, it tends to 0 because in this point, this J, this derivative J of R is 0. So away from our wormhole throat, it is some positive constant, and exactly in the point of throat, it is 0. This means for this equation that T11 minus T00 for this time-like vector is negative. So in other words, it means that fx is negative. So if we take Lagrangian in the form of just a function of derivatives, it will be ghost scalar field. So this combination will be negative near the throat. And for regular matter, it will be positive. So, but it will always be singularity. So the solution in theories with third derivatives are always unstable. actually there is a theorem that if we break null energy condition in series with first derivatives, we always get instability. So we have possibilities to go to higher derivatives or maybe even non-locality. Also, lately there are famous solutions with fermions, or in other way, Casimir energy, but it's involve quantum effects. I refer to papers from Aldacena and others. So we try Horndeski series. We know that it can break neck in a healthy way because it's Lagrangian involve higher derivatives. Still, equations are only second derivatives. So this is Horndeski theory, and this addition is beyond Horndeski. Well, for us, there is almost no difference because all the perturbation contains on the second order. So after all, it's okay for us. Even host is okay, but just a little more complicated to study. Even host is okay. So since we know that in bouncing scenarios in cosmology, beyond Horndeski theory worked well, and we know that wormhole looks like bounce. You see that this metric for bouncing scenario could be made by reparameterization to look almost like the metric of wormhole. And profile of bounce looks like profile for wormhole. And in bouncing scenario in cosmology, we know that there is no go theorem. In Horndeski theory, it breaks. In beyond Horndeski, there is a possibility for stable bounce and even subluminal stable bounce. And beyond Horndeski worked well for cosmology. So we try the same for wormhole. So indeed, there is a no-go theorem for wormhole in Horndeski. Indeed, it breaks in beyond Horndeski. And by this time, there was already a stable solution for wormhole. And to announce, now we also got the angular stability for this wormhole. Still, we didn't try tachyon instability. It's much more involved, and it's for the later work. So in Horndeski and beyond Horndeski, our rule is 3 degrees of freedom. In cosmological scenario, it's 2 tensor and 1 scalar, but in spherical symmetric, it's 2 even and 1 odd. So parameterization of metrics looks like this. And background field we take only as a function of R. We also do not try this scalar field that depends on T. For instance, because we're considering not shift symmetric, but general Horndeski theory. So it's much more convenient to take the function of only radius linearized metric. And we decompose into spherical harmonics like Reggie-Wheeler and study odd and even parity modes independently. So actually, this was done for Horndeski theory in this paper in well, almost 10 years ago. So this is for odd-parity sector. There is no perturbation for scalar field, and we take only this H0 and H1, and H2 we put to 0 by gauge choice. Then we have this action. Yeah, this is the paper I'm talking about, 2012, and we integrate out non-dynamical degrees of freedom and get the action for this dynamical Q. After it, in odd-parity sector, stability conditions look like this. The same can be done in even-parity sector. Again, we took these guys to 0, and only these 4 are present. This is the action. We integrate out and get the action for dynamical 2 even-parity modes. This was done in this paper. Well, actually, it was done for Horndeski theory, and in later papers we did the same for beyond Horndeski theory. It's very similar, just these coefficients depend also on beyond Horndeski functions. So this action in even-parity sector again requires these matrices in high momentum regime, only K and G, to be positively definite. So, for instance, these relations are sufficient. And from odd-parity sector, we already have these relations. This is non-singularity of our background. And in Horndeski theory, we get this left side. And in beyond Horndeski, it's almost the same, but slightly changed by this additional factor D, which depends only on beyond Horndeski function. So what does this relation tells us? It tells us that since f is greater than 0, then 2p is greater than f and also greater than 0. That means that we have a function which derivative is greater than 0 and its numerator is greater than 0. It can't cross 0. And this is a source for no-go theorem. Unlike beyond Horndeski case, where numerator can be 0, in case when h, which is greater than 0, equals to d, which is almost arbitrary. So how the no-go theorems work? So we have a function which derivative is positive, but this function can cross 0. So if this function is defined from minus to plus infinity, and its derivative is greater than 0, then we should have f equals to 0 at some point. You see, for example, if f is smaller than 0 at some point, we go forward in our x variable. And since the derivative is positive, at some point it should cross 0. Otherwise, if it's positive at some time, we go backwards in x derivative, and f should cross 0 at some point. So if our function cannot cross 0, since numerator is positively definite, so that means that we have a contradiction. It's a no-go theorem. But it's only from minus to plus infinity. So if we want only locally stable, then Horndeski is okay. So no-go theorem for wormholes was proved in these papers, and later it was found out that in beyond Horndeski theory, it is actually possible to avoid this no-go theorem, exactly like in cosmology scenario. So this is our action, and what was new is that it also there is this part M matrix. This looks like mass matrix, but it contains L square part, which is can be interpreted as angular momentum matrix. So it's like angular derivatives, right? So this part of M, which is proportional to L squared, is also should be greater than 0 in high momentum regime. So if we consider modes that are not only radial but angular also, and in principle just only angular momentum modes, this derivative could be 0 for them, but instead this part should be big. So we also managed to construct a solution in which this part of M matrix is also positive definite. So what did we do? We take our Lagrangian, general Lagrangian for beyond Horndeski theory. We take P of R background solution as we want. We took it P equal to R. It always, on any solution, we can make it to anything we want after field reparameterization. So when we reconstruct Lagrangian, we first take our background as something, also A, B, and R as a function that suitable for wormhole. And then we find Lagrangian functions in a way that this and this inequalities are satisfied. So we managed to get such a Lagrangian that this K11, G11 greater than 0. This guy is also greater than 0. And even this part of M and that M greater than 0. So here it's only high L parts, but still these terms are very complicated. I couldn't even fit them on a slide. So yeah, so these guys are not that big. This is K, and that K, that's for dots, and G for R derivatives. So this is that they're greater, well, on this graphics, see that they're greater than 0, but also there are some bad points. So you see that here, for instance, are always two infinities, and this is due to this term in denominator. And it turns out that this denominator should always cross 0. So these infinities are inevitable. And still, because it's squared, it doesn't affect the that is greater than 0, but we get infinities in some points. It's not good, but as we know, in cosmology there is this gamma crossing scenario, which is fine because it is only singularity in unitary gauge, and as we know, in Newtonian gauge there is no gamma crossing for the same solution, that everything is okay. So here the situation looks very similar. We have singularities in quadratic action coefficients, but speeds of sound, these two are for even sector mode. For the odd sector, it is equal just to 1 everywhere. So speed of sound everywhere are finite, and infinities in these coefficients are just, we suppose that they're just gauge artifacts. Another bad point is 0 here. So zero is this in quadratic action coefficient might be very bad because infinity is potentially infinitely small coupling, weak coupling, and 0 in quadratic coefficient is supposedly infinitely strong coupling. That's not good. And this is due to this G prime and G prime here in determinants. So, of course, the speed of sound is again finite, but 0 is not very good in this coefficients. Still, we think that it is artifact of our gauge choice. So let me remind you, this is even-parity sector, and our gauge choice is like this. So what are the gauge transformations that allows us to do this? And let's look at the last one with k. We see that there is g prime in this k function. So this t, theta, and r are gauge functions, and gauge function is multiplied by g prime. That means that near the wormhole throat, such gauge with k equals to 0 is impossible. We can't make k equals to 0 exactly at wormhole throat. And that's why we think that that problem with j prime in determinant of those coefficients is due to the bad gauge choice. So this 0 is supposedly due to wrong gauge choice. So let me go to conclusion. I have like 3 minutes. So what is required right now is also to study different gauge choice, because well, the gauge that is we took on first glance to study wormholes is not very good. It's actually fine everywhere except for several points maybe, but probably we could find everywhere good gauge, or just study these points directly in different gauge and understand if the solution that we find is actually okay, or this zeros and maybe infinities are actually some problems like strong coupling or something. So still we have not addressed the tachyonic instabilities, because, well, even L squared part of this M matrix is enormous, and the tachyonic part, tachyonic instability requires the study of all the matrix M, and this is huge. But still we think that, well, it will take time, but I think that we'll, in the end, we will manage to overcome this problem. So right now there are classical spheric symmetric wormhole solutions without ghost or gradient instability, both radial and angular. So in high momentum regime, apart from maybe these problems in several points with gauge, but, well, I believe that it's just an artifact of gauge. Apart from these problems, we have wormholes which is stable in high momentum regime. And, well, still it's not totally healthy, but we'll see. Thank you for your attention.
Thank you very much, Sergei. Any question? Okay, so Chae-Yoon Chen, please.
Oh, yes, thank you for the talk. In one of the slides, you have a sentence saying that a healthy solution requires the correct sign of kinetic and gradient signatures. And yeah. I'm wondering, I suppose that the opposite direction should be wrong. I mean, correct, if you have a model with correct kinetic term and correct gradient term, it doesn't really guarantee that the solution is healthy. But so far, I don't know. Is there any counterexample of this?
Let me go back. You mean this, right?
Yes,
but,
yes.
Yeah, so, well, if we don't have this part, okay, then, or in other words, we have high momentum regime, if we want solution to be stable, we require this UV greater than 0, right?
Yes.
So by healthy, I mean stable right now.
Yes, right.
So I don't understand the question. So
I mean, is it possible to have a model that U and V are both positive, but in the end, you get an unstable solution?
Well, that depends on what you mean unstable. If U and V are greater than 0, sufficiently greater,
yes.
then and suppose you don't have this W, then this is a stable solution.
Okay.
Okay.
So it still depends on
at least linearly stable. Of course, there could be some nonlinear effect, or maybe even more perturbative effect, but this is a linearly stable solution.
Okay.
Except for the this W, which if it is less than 0, there could be tachyonic instability, which is only viable for low momentum. So, for instance, in cosmology scenario, there is in unitary gauge there is no this W, so only these two coefficients. But in wormhole, because it's static solution, then even low momentum regime of instabilities will have infinite time to destroy it. So in wormhole's solution, we need to worry about this W.
I see. Okay. Thank you.
Alex?
Hi, Sergei. Thanks a lot for very nice and pretty technical overview. You just mentioned in 2 points that fermions would also do the job to create a wormhole. I'm a bit puzzled. Probably not standard fermions, no?
Yeah, it's a paper by Moldavtseva and others about they have well, they claim they have a stable wormhole. And as you know, fermions have negative energy.
But they don't, right? We know this is in our piece of metal. They always have positive energy.
No, that's quantum. That's quantum effect. That
so it's not. So it's a purely quantum or Casimir or what?
Yeah. It's as I told, it's quantum energy of a fermion, right? Casimir energy, yeah. So
okay.
Casimir energy of fermion. So it's exactly
okay.
what
I thought you treated them separately. Okay. And another question is a very simple one. So for bounds, so formally speaking, if we have non-minimal, just non-minimal coupling, let's say phi couples to whatever, phi squared couples to R, then it's possible to have a bounce in this Jordan frame. Though, okay, somewhere you would have probably some singularity, but definitely, sure. But people probably studied this till death for wormholes, right? I would suspect.
I'm not sure because, well, in cosmological scenario, it seems okay to study partly stable solutions because, well, you have some evolution. And then you usually say that you have reheating something else, and later you have different theory, and you don't care more about your stability because well, it's different theory. Who cares what's there? And in wormhole scenario, well, because it's static, you usually consider the whole universe. It should be stable everywhere. Otherwise, you will have wormhole which is stable near the throat, for example, but unstable somewhere else. You can say that there is different theories there. It's well, it looks unnatural, but I don't. Well, the question I don't know. Maybe there was some, but I'm
right
not.
Because you see, the simplest way to avoid it would be like imagine there is some instability happening in some radius away, some radial distance away from the throat. But you can always say that in reality there's cosmological expansion, and therefore this asymptotics is not right anymore, and you wouldn't care. something like that.
Yes, that's right. But in this case, you should consider this cosmological asymptotic as well. So it's time and
Right.
R dependent. Yeah.
Right. That becomes, of course, much more complicated. But I mean, formally speaking, one could use the same logic as for cosmology, and just in that case, I would suspect that there would be tons of works. I mean, like old papers on this non-minimal gravity with wormholes.
Yeah, actually, there are papers. For example, by our colleague in INR, Mironov, he told recently, he considered solutions for wormholes, which is also asymptotically de Sitter. So it's this Reisner-Nostern de Sitter solutions. But he didn't care much about stability. So that's a different story.
Okay. Thank you.
Okay, so no more question. Okay, Sergei, thank you. And so let's thank all of the speakers in the morning session.